Okay, dear students, welcome to my YouTube channel. Today we will discuss something about the magnetic susceptibility for uh, ferromagnetic materials. In previous lectures, we have calculated the same parameter for diamagnetic materials and paramagnetic materials. Here in this lecture, we can calculate the same parameter for ferromagnetic materials. That is magnetic susceptibility for ferromagnetic material, that is chi. So here I can repeat, in chi was equal to C upon T for paramagnetic materials. This law is called as Curie law because this concept was first given by Pierre Curie. This concept of temperature dependence of magnetic susceptibility was first given by Pierre Curie and is called as Curie law. Here you see the temperature variation of susceptibility can be seen graphically as if it is temperature in Kelvin along x-axis and this is the susceptibility along y-axis. So the variation of chi with temperature is like this. If we increase the temperature of a specimen, the magnetic susceptibility increases. That is, the magnetization within the material increases with the decrease of temperature. So there's the inverse relation between chi and T. So this law was modified for, this is for paramagnetic materials, this was modified for ferromagnetic materials by Weiss. That is called as Curie-Weiss law. Curie-Weiss law, and can be written in modified form for ferromagnetic materials, that will be C upon T minus theta C. So this is the modified form of this Curie law for ferromagnetic materials, because ferromagnetic materials are strongly attracted in magnetic field as compared to paramagnetic materials. So here the parameter theta C, this is called as Curie temperature. So if we plot this law graphically, so this law is like this. This is the graphical representation of this law. Here it is chi in y-axis and temperature in Kelvin along x-axis. So if we decrease the temperature, so there is a critical temperature, Curie temperature, theta C. So on the basis of, if T equal to theta C, if these are equal, then chi will be infinite. Here, if T is equal to theta C, so the magnetic susceptibility, magnetization produced within the material will be infinite. At T less or equal to theta C, that means temperature is in this region, this lies in this region. So this is called as complex behavior. So if this is called as complex behavior, but here there is spontaneous magnetization. So if T is greater than or equal to theta C, so magnetization, that is magnetic susceptibility, will be small. Because ferromagnetic materials are like iron, they have permanent magnetic moments in absence of magnetic field also. So if we plot this graph, here it is temperature in Kelvin, here this is magnetic susceptibility in y-axis. If it is inverse, that is 1 upon chi, then it will be straight line, and which is whose initial point coincides with the origin, starts from origin. So this is the representation of this. This is for paramagnetic. So for diamagnetic, if it is 1 upon chi, and here it is temperature in Kelvin, so it will be start here from temperature axis, here it is theta C. So this is for ferromagnetic. So 1 upon chi will be linear and chi versus T will be parabolic. So it is parabolic. So 1 upon chi with temperature change is straight line, which starts from origin for paramagnetic, and it starts from somewhere theta C from temperature axis for ferromagnetic materials. So therefore, before going to discuss these ferromagnetic materials, what they are and what is the importance of these materials, so we want to first calculate the magnetic susceptibility for ferromagnetic materials. Here you see, the modification was given by Bayes, and so in absence of any external field, there is spontaneous magnetization. So there is a internal magnetization. There is internal magnetization. In absence of magnetization, in absence of B, external magnetic field, so we can write H internal will be equal to lambda times M. This lambda is called as molecular field coefficient. Therefore, if we take a ferromagnetic material, it is like this. So ferromagnetic materials, so there are, because in case of ferromagnetic materials like iron, ferromagnetic materials are like iron, cobalt, nickel, and some oxides also, that is chromium dioxide. So these are the ferromagnetic materials. So in these ferromagnetic materials, there are unpaired electrons actually, because we can take into account the main the main contribution in magnetization is due to the electron spin. If there are unpaired electrons present within the material, so there is a net magnetization. So without applying any external field, there is net magnetization present in the material, that is called as spontaneous magnetization. So this is due to the unpaired electrons, that is supinous. So these supinous are like this. In some regions they have the same alignment, in this region same alignment. So these same alignment regions are called as magnetic domains. So in one domain there are near about 10 to the power of 9 to 10 to the power of 15 atoms. 10 to the power of 9 to 10 to the power of 15 atoms can participate in one domain. So here these domains are separated by some boundaries. These are called as domain walls. Or Bloch walls. So therefore there is some internal field, so we can write H internal as lambda times m, that is some magnetization present within the material due to presence of these domains, magnetic domains, and here lambda is the molecular field coefficient. So the effective magnetic field intensity will be equal to HA H plus H internal. This is due to the magnetization occurs due to the applying field, and this is presence of these domains HI. So we can write, we know the magnetization M will be equal to N mu M into Langmuir's function. So N mu M will be equal to A upon 3. So this will be equal to N mu M. So value of A will be mu M B upon 3 kBT. So you know these parameters I have already discussed in previous lecture. So this is the magnetization M. So we can write this equation as magnetization M will be equal to N mu M square upon 3 kBT into B will be equal to mu naught H, that is mu naught is here, H is here, that is H effective. So we can write this as N mu M square mu naught upon 3 kBT, and the value of HE will be here, that is H plus HE, HI internal. So magnetization M will be equal to N mu M square mu naught upon 3 kBT. This will be equal to H plus HI. HI will be equal to lambda times M. So we can write here lambda times M. So magnetization M will be equal to N mu M square mu naught upon 3 kBT. Here H plus lambda times M will be equal to N mu M B N mu M, and mu naught in place of B we can write mu naught H, but mu naught is here 1 because this is inside the material, so that we can write H upon 3 kBT. So this equation can be written as magnetization M will be equal to N mu M square. H will be common here, H upon 3 kBT. There remains 1 plus lambda N mu M upon 3 kBT. So we can write it as N mu M square H upon 3 kBT. This will be written as 1 minus lambda times N mu M 3 kBT. Because if it is in numerator, that is power minus 1, so we can use binomial theorem and we can get back this equation. So M will be equal to here N mu M H square is here 3 kBT. kBT will be equal to T will be given inside, that is T minus lambda N mu M 3 kB. Because T is here, T and T will cancel each other. So magnetization will be equal to related to the magnetic susceptibility chi as M upon H. So H and H will cancel, there remains N mu M square, and there is one more parameter, that is mu naught. Also mu naught is here, and mu naught upon 3 kBT. Not here T, because T is here now, so T minus lambda and mu M upon 3 kB. This will be written as chi, because this is constant, all constant. There is a single constant, that is C, that is called as Curie constant, upon T minus this, all this thing will be equal to theta C. Theta C is called as Curie temperature, and its value will be equal to N mu M upon 3 kB. It has dimensions of temperature. So this is the given law, that is modified form of the magnetic susceptibility, that is Curie law, that is called as Curie-Weiss law. So ferromagnetic materials are those materials which are strongly attracted in magnetic field. So they also follow the hysteresis curve. Hysteresis loop. What is this loop? For example, if this is actually a BH curve, also known as BH curve. So here, if it is external magnetic field intensity, here it is magnetization M in y-axis. If we place a ferromagnetic material in a magnetic field, so if we increase the intensity of a magnetic field, the magnetization of the material is like this. The magnetization of the material increases and reaches to a constant value, that is saturation. After that, if we increase the field, there is no more magnetization found within the material. So this is called as saturation point. So after that, if we remove the magnetic field. For example, if we touch an iron nail with magnet, it will, after removing the magnet, it will be magnetized even after the absence of magnetic field. So it will become a magnet because some domains tends to align themselves in a particular direction, so there is a net magnetization. So here you see, if we reduce the magnetic field or remove the magnetic field, it will be like this. So first of all, that is here. That means if the magnetic field intensity is 0, there is magnetization present within the material. So the ferromagnetic material is magnetized even after the magnetic field, external magnetic field is 0. There is no magnetic field. So this portion of magnetization is called as retentivity. So if we want to demagnetize this material, because it is magnetized here, so you have to apply the external magnetic field in reverse direction. For example, if this was south pole, this was north pole, and you have to change the polarity, that is, this is north pole and this becomes south pole. So that due to this due to applying this reverse magnetic field, it will be reached, the magnetization will be 0. For reaching the 0 magnetization, that is called as coercivity, or we can say coercive field, because due to which we can demagnetize a material. So if we increase the magnetic field intensity in reverse direction, it will be reaches to a saturation again, just like this, but in reverse direction. And after that, if you remove the magnetic field, it will be like this. And after that, it is also called the retentivity. After this, we want to demagnetize it completely, so it will be here. So magnetization will be 0 at this field is called coercive field, and after that, so this loop, complete loop, that is O, A, B, C, D, C, D, E, and F, and A. This loop is called as hysteresis loop, and this loop cannot be found in case of paramagnetic materials and diamagnetic materials cannot show hysteresis loop. This loop is found only in case of ferromagnetic materials. And the area under this loop will give us loss of energy, or we can say work done in magnetization and demagnetization. This will give us the amount of energy or amount of work done will be equal to any. So after that, this the area under this loop will give us the loss of energy, or we can say work done. So there are some materials, ferromagnetic materials. These are hard and soft ferromagnetic materials. Soft, in case of soft ferromagnetic materials, they have less area in BH curve, that is hysteresis loop. Area under the hysteresis loop will be small in case of soft ferromagnetic materials as compared to the hard ferromagnetic materials. The soft have less area in hysteresis loop as compared to hard materials, a hard one. So both of these ferromagnetic materials, that is soft and hard materials, have their own uses in many of the applications. Here you see the hard ferromagnetic material. Here I can write short form, that is ferromagnetic material, and soft ferromagnetic materials. Here you see the hard ferromagnetic materials are cobalt, nickel, iron alloy. This is the hard material, and the soft materials are soft iron or iron nickel alloy. These are the soft ferromagnetic materials. These are hard ferromagnetic materials, or we can see here nickel steel is also a hard material. So both of these have their own uses. Hard ferromagnetic materials can be used as permanent magnets. And the soft materials have their uses in, for example, core in transformers, and they have used in data storage devices. In many computer applications. So I hope you understand this lecture, and thank you.